When the ground shakes, news headlines quickly report magnitude 6.4 quake, epicenter near Los Angeles. But hold on, how do scientists actually know where that earthquake began deep inside the Earth? Hey everyone, welcome back to the channel. Today, we're diving into how scientists pinpoint the exact location of an earthquake. And if you love learning how our planet works, make sure to hit that subscribe button and let's get started. Every earthquake begins deep underground, at a point called the focus, where stress in the rocks is suddenly released. The spot on Earth's surface directly above it is known as the epicenter. When an earthquake strikes, seismic waves radiate out in all directions from the focus. And it's these waves, recorded by instruments called seismographs, that help scientists figure out where the quake began. So, what exactly are seismic waves? They're vibrations that travel through the Earth, and they come in two main types: body waves and surface waves. Body waves include P waves or primary waves and S waves or secondary waves, while surface waves include L waves or love waves and R waves or Rayleigh waves. Each of these moves in a different way and travels at a different speed. P waves, or primary waves, are compressional. They push and pull the ground back and forth, moving the fastest, at speeds between 1.5 and 8 kilometers per second. Whereas S waves, or secondary waves, move more slowly, about 60 to 70% slower than P waves, and shake the ground side to side. But L and R waves, the surface waves, are the slowest and take the longest route, moving along the Earth's surface instead of through it. These are the waves that cause most of the damage during earthquakes. However, when it comes to locating an epicenter, scientists mainly focus on P and S waves because their difference in arrival times is the key. Since P waves travel almost twice as fast as S waves, they arrive at a seismograph station first, followed moments later by the slower S waves. This time gap between their arrivals tells scientists how far away the earthquake occurred. To make this easier, seismologists use something called a travel time curve, a standardized reference graph that shows how wave travel time changes with distance from the earthquake's epicenter. These travel time curves aren't made from scratch each time. They're based on extensive seismic data collected from thousands of earthquakes around the world and represent the relationship between travel time and distance for both P and S waves. To ensure accuracy, seismologists rely on well-established Earth models, such as PREM, the Preliminary Reference Earth Model, and IESB 91. These models are built from millions of seismic observations and take into account Earth's layered internal structure and velocity discontinuities, like the Mohorovičić discontinuity, or MOHO, where seismic wave speeds suddenly change. The travel time curve built from these models helps scientists figure out how far a seismic station is from the earthquake's epicenter. Here's how it works visually. On the graph, the horizontal axis shows the distance from the epicenter, and the vertical axis shows time. There are two separate travel time curves of P and S waves, one for each wave type. As the distance increases, both curves rise, showing that the farther a station is from the epicenter, the longer it takes for the waves to arrive. Now comes the key step in calculating the epicenter of a recent earthquake. From the seismograph recording, scientists measure the time gap between the arrival of the P wave and the S wave. This is called the S minus P time. To find the epicenter, The S-P interval is drawn as a vertical line segment along the time axis on the travel time curve, so that one end aligns with the P-wave curve and the other with the S-wave curve. By dropping a line straight down to the horizontal axis, scientists can locate the distance to the epicenter from that seismic station. This method reveals how far the earthquake occurred from the seismic station, but it doesn't reveal the direction. Here's where the magic of triangulation comes in. Imagine you have 3 seismic stations on a map. From each station, scientists know how far away the earthquake was, thanks to that S-P interval we just measured. Now, picture drawing a circle around each station. The radius of each circle represents the distance to the earthquake's epicenter. One station tells you how far the epicenter is, but not where. 2 stations narrow it down to 2 possible points. And the third station? It pinpoints the exact location where all 3 circles intersect. The one spot, that's the correct distance from every station. And that's how scientists can say, with precision, the epicenter was near Nepal. But here's something fascinating. Not all earthquakes start at the same depth. The point inside the Earth where an earthquake actually begins is called the focus, and the focal depth is the distance from the Earth's surface down to that point. Now, figuring out how deep a quake occurred is trickier than finding its epicenter. Scientists estimate this depth by comparing seismic wave patterns from multiple stations and running mathematical models to see which fits best. Even then, the results aren't perfectly precise, but they're good enough to reveal some patterns. Most earthquakes, about 75% of them, occur quite close to the surface, usually no deeper than 10 to 15 kilometers. But a few reach astonishing depths, as deep as 670 kilometers beneath the surface. Based on how deep they start, earthquakes are classified into 3 main types. Shallow focus quakes, that are 0 to 70 kilometers deep. These are the most common and the most destructive. Intermediate focus, 70 to 350 kilometers deep, and deep focus earthquakes, 350 to 670 kilometers deep. Shallow focus earthquakes make up about 85% of all the energy released worldwide, whereas intermediate ones contribute around 12%, and deep focus quakes just 3%. Why the difference? It's because deep rocks behave differently under such high pressure and temperature. They tend to flow and bend instead of breaking. That means they can't store or suddenly release energy the way brittle surface rocks do, making deep quakes far less frequent. Today, locating an earthquake is faster and far more accurate than ever before, all thanks to modern technology. Across the world, dense seismic networks use compact, ultra-sensitive sensors, like MEMS devices, that can detect even the tiniest tremors in real time. Artificial intelligence and machine learning now play a huge role too. They automatically pick up the arrival of P and S waves, analyze their patterns, and calculate the epicenter within seconds of a quake. Meanwhile, satellite systems such as interferometric synthetic aperture radar, or INSR, measure minute changes in the Earth's surface from space, confirming exactly where the ground shifted. And here's something truly cutting edge. Fiber optic cables, the same ones that carry internet data, are now being used as massive seismic sensors, detecting vibrations across entire regions with astonishing detail. Together, these innovations have revolutionized seismology, making earthquake detection faster, smarter, and more precise than ever before. So next time you hear a headline say, A magnitude 7.1 earthquake struck with an epicenter near Tokyo. You'll know exactly how scientists figured that out from seismic waves, travel time curves, triangulation, and now powered by cutting-edge sensors, satellites, and AI. If you found this explanation fascinating, don't forget to like, share, and subscribe for more Earth science stories. Thanks for watching and stay curious.